Hello everyone, welcome to Technologies Discussion Channel. Today, I'd like to continue the discussion on antenna. Okay, on my previous few discussion on antenna, I have introduced key parameters of antenna. Okay, so this video will be the same. This video, I'm going to introduce antenna impedance. Okay, what is actually antenna impedance? Okay, so under this antenna impedance, we have three things. Okay, so basically we have radiation resistance, loss resistance, and reactance. We are going to take a close look. What are all these three things that will affect the parameters of antenna? This will be the Part 8 series discussion on antenna. So guys, if you're keen to know more about antenna, okay, please take a look on the playlist under the description. Over there, you will be able to find a series of discussion on antenna. This is my email. If you have any question regards on this discussion, please drop me an email. Okay, or if not, if you want to have a faster response, you are always welcome, okay, to ask me through the comment. Okay, before I continue, I'd like to urge you guys to help this channel by like this video. For those who are new to this channel, please consider to subscribe and turn on your notification bell. Once again, thank you so much for strong support. These are all the key parameters of antenna that we will be so-called discuss. We have done the radiation pattern, gain, directive, beam width, and polarization. This video, as mentioned earlier on, I will be focusing on antenna impedance. Okay, although the phenomenon of an antenna converting electric current into EM wave is fascinating. Okay, in many analyses, basically we can simply model the antenna as an equivalent impedance. Okay, for example, a 50 ohm resistor. Okay, in this diagram here, you can see that this is a antenna. Okay, and from here you can see that we can easily model this as a 50 ohm resistor, for example. So basically, this will simplify the analyze of this antenna, simply by convert the antenna into a impedance. Okay, for the off-the-shelf antennas, the manufacturers specified the antenna impedance in the datasheet. So in short, those the antenna that you can actually bought, basically the manufacturer would like to simply indicate the antenna impedance in the datasheet. However, basically for customized antenna, the impedance must be measured or simulate. Because for customized antenna, the impedance basically will change with frequency. So hence with this, we must be sure. So therefore, we need to do a comprehensive measure or at least simulate the outcome of the impedance for the antenna. The antenna impedance remain the same in both receive and transmit mode. Nowadays we have this transceiver, which means that it's capable to transmit and also receive. Hence, for this antenna impedance, they are the same, whether they are in receive mode or the transmit mode. So the key thing about this antenna impedance is actually known as radiation resistance. So this is the key thing, that will determine the antenna impedance. So basically, we are going to take a close look on this radiation resistance, on this video. The antenna impedance is in fact a measure of a resistance of an antenna, that is actually present to the flow of electrical current at a given frequency. So in short, basically we can measure the resistance. How can we measure the resistance is basically how well the electrical current flow with the respect of frequency. As I mentioned earlier on, basically for impedance, basically they actually vary with frequency. So therefore, for antenna, basically we measure what will be the resistance of the antenna with the flow of the electrical current and at a particular frequency. It is actually a complex quantity, which means that you actually have a real part and we also have an imaginary part. So basically for antenna impedance is a complex quantity. As I mentioned earlier on, it consists of resistive part, which is the real component, and also the reactive part, which is the imaginary component. What is the resistive component, which is the real part? So this part of the impedance actually dissipate energy, which means that this impedance, they actually will radiate out energy in short. So in general, basically is maybe in the form of heat. Basically this will be under the loss resistor, or radiate electromagnetic wave. So basically this will be under the radiate resistor. So basically, in short, for this resistive component, they maybe have two functions. One is the loss resistor, another one is the radiate resistor. Okay, it reflects the actual power that is radiated up by the antenna. Okay, so basically this is the radiate antenna. Okay, a well-designed antenna might have a resistive component of 50 ohm. Okay, so for RF, typically we want to standardize. So basically we will actually use this 50 ohm. Okay, mean that it is able to optimize to have an effective power transfer. Okay, when we actually connect them to a transmission line with a characteristics impedance of 50 ohm. Okay, remember this. Okay, in order to have maximum power transfer, in order to minimize reflection, okay, basically we need to be matched. How to be matched is, for example, okay, let's say the resistor of the antenna is 50 ohm, then we want the characteristic line or the transmission line also to be 50 ohm. So once we actually achieve this, then we have minimum reflection, and therefore we are going to have maximum power transfer. As for reactive component, okay, which is the imaginary part, okay, so this part of the impedance store and release energy, okay, without dissipate it, okay, which means that they actually store or they actually release it without really consume the power. Okay, it is typically associated with inductance, okay, which is the positive reactance, or capacitance, which is the negative reactance. Okay, the reactive component actually vary with frequency, which I have highlighted many times, and this actually will affect how well the antenna is tuned to a particular frequency. Okay, an antenna serves as an interface between circuit and space, which I have highlighted. The key role of antenna, what they do is basically they convert the electrical signal into electromagnetic wave. So basically, under the electrical signal will be the circuit, under the electromagnetic wave will be the space, which is air. Okay, basically they facilitate the transfer of power, okay, between the communication medium, okay, for example, air for this case here, and the transmitter or receiver. So basically, in short, antenna is a middleware, okay, in between the communication medium, okay, either for transmitter or receiver. So basically, they will behave slightly different in terms of characteristics, but not on impedance. Impedance will be the same, okay, as he mentioned here. Okay, the antenna impedance acts as either the load for the transmitter or the input impedance for the receiver. Okay, so basically, you can imagine that when you actually transmit, okay, and the antenna actually like a load. Okay, basically the antenna will be at the end. Okay, however, when we actually build a receiver, the antenna is right in front of every stage. So basically the antenna actually become a input impedance for the receiver. Okay, it mainly consists of three components. Okay, first will be radiation resistant, second will be the loss resistant, and last but not least, reactance. Okay, the resistance observed by the transmitter or receiver at the antenna, okay, will be equal. Okay, so basically the sum of radiation resistor and loss resistor. Okay, so basically the antenna resistance or impedance basically consists of the sum of radiation resistant and also the loss resistant, and they may also include a reactive component. Okay, so basically I specified the word may. Okay, basically if we do a so-called match, then we will be basically remove the reactive component. However, in the reality of an antenna, it may be include the sum of radiation resistor, loss resistor, and also the reactive component. Okay, when there is no reactive component, the antenna is considered resonant. Okay, so once it resonant, which means that maximum power transfer actually occur, okay, between the antenna and the transmitter or receiver. Okay, when the impedance seen from the antenna terminal is the complex conjugate of the antenna impedance, then we are able to have this maximum power transfer. Okay, it is important to match the transmitter to the antenna, okay, not only to get maximum power transfer, okay, beside that, okay, to get maximum power transfer, we actually also get the best attenuation of harmonics. Remember, harmonics is undesired and we need to remove away harmonics. So basically, we want to attenuate the harmonics as much as possible. So basically, in order, beside to do maximum power transfer when we actually match, okay, when we actually match the attenuation of the harmonics relative to the fundamental frequency is also maximized. Okay, when the transmitter is matched to the antenna. So in short, when it's matched beside maximum power transfer, we also will suppress the harmonic, okay, which is a very important point in meeting the spurious radiation. In short, okay, for whatever so-called electronic device that we build. Okay, remember, because of EMC, we are not able to transmit, okay, outside the desired frequency. So basically, anything that we actually transmit at the undesired frequency, it become so-called, is fall under harmonics. And then basically with this, we may not be able to pass the EMC test. And because of this, okay, we need to ensure that we pass the test by attenuate all the harmonics, and hence it's very important to have an impedance transformer, okay, for the transmitter to the antenna. So basically, this is what I mean. Okay, the radiation resistor depend on the proximity of the antenna to conducting and insulating project. Okay, for example, an antenna, they basically, when they are very near, for example, a conducting material, it may affect the radiation pattern. Okay, so therefore, anything that is close to the antenna, it may affect the performance. Okay, this is in particular, it also depends on the height of the antenna from the ground. So basically, the ground is always like a ground. I'm not sure how to rephrase this. Basically, a ground basically will be the reference point. So basically, the height of the antenna will be very crucial. Okay, because if it's too so-called too short, then it will be very near to the ground. If it's very high, then it will be more desired. Okay, thus the antenna matching circuit of a transmitter, okay, with integrate antenna that is intended to be handheld should be optimized for the antenna impedance in a typical operating situation. In short, okay, the antenna matching basically need to optimize based on your use case. Okay, whether it's a handheld, then you need to do it handheld, or actually mount on a so-called a rooftop, etc. Okay, before I continue, if you have learned something from this video, okay, please consider to like this video. Please help this channel. Okay, smash the like button now. If you have learned something again, okay, please consider to subscribe and turn on your notification bell. Thank you. Okay, let's quickly go through the three type of impedance. The first one, which is the radiation resistant. Okay, so come to the definition of radiation resistant. It's basically is a conceptual resistor, which means that this resistor actually don't actually exist. Basically, is a theory resistor or something that we imagine this resistor. Basically, they represent the resistor as an antenna exhibit due to the radiation of electromagnetic wave. In short, this radiation resistor will affect the radiation of electromagnetic wave. Okay, later on we are going to take a close look. Okay, basically this indicate how effectively an antenna convert input electrical power into radiate electromagnetic power. So in short, this resistor, radiation resistor, okay, basically will show how effective an antenna actually convert the electrical power into electromagnetic power. So basically, we would like to take a look on this radiation resistor, okay, later on, to understand how efficient, okay, that we can actually convert the electrical power into electromagnetic wave power. Explanation. Okay, when current flow through an antenna, okay, so basically for an antenna, basically you run a current, okay, part of the electrical energy is radiated as EM wave. So when there's actually a current flow, okay, basically like a eddy law or something like that, basically the current flow actually create a EM wave, and basically they radiate out. Okay, while some may be lost as heat, okay, or through other mechanism, okay, the radiation resistor measure the portion of resistor that is responsible for the radiation of energy. So in short, okay, as I mentioned earlier on, radiation energy can actually depend on radiation resistor. Okay, so the SI unit will be ohm. Okay, how we actually calculate the formula, okay, to calculate this radiation resistance is actually shown over here. This will be the power that is actually radiated up divided by I squared. So basically, in short, you can see that the radiation resistor is proportional to the radiation power. So basically, in short, the higher the resistor, the more power that I will be able to radiate out, as you can see from this formula. Okay, a typical example for a half-wave dipole antenna, they basically has a radiation resistor of around 73 ohms. Okay, so this will give you some indicative, okay, roughly what will be the value for the radiation resistor value, okay, for this half-wave dipole antenna. Okay, next will be on the loss resistance. Okay, so come to the definition first. Okay, the loss resistance actually refer to the resistor caused by non-radiative loss. Okay, basically earlier on we talked about radiation loss. Okay, sorry, radiation resistor, but over here we are going to consider any other thing, okay, beside the radiation resistor or radiation power. Okay, so basically this include the heat dissipation, okay, which means that when we actually convert the energy from one form to another form, from the electrical signal to EM wave, for example, okay, heat may be generated and this become a loss resistor because this is undesired. We actually lost some of the power. So basically, this is what it means. We beside this heat dissipation, we also have this, for example, conductor loss or dielectric loss. Okay, so basically, in short, we have also these two form of loss, and the resistance from imperfect conductor, which I mentioned earlier on, and all the losses that is actually caused by nearby object. Okay, so basically, this loss resistor is a resistor that account for all the kind of loss. Okay, basically minus away the radiation loss, all kind of loss will be accounted by this loss resistor. Okay, this resistor result in inefficiency in the antenna operation, okay, by consuming power that is instead dissipated as heat rather than being radiated. Okay, so remember this, the key thing of antenna is we want to radiate as much as possible. However, we know that, okay, there's no 100% radiation energy. We know that some may be dissipated as heat, some may be dissipated as conductor loss, dielectric loss, etc. Okay, so therefore they are all lumped under this loss resistance. Okay, the SI unit will be still the same, will be ohms. Okay, there is no specific formula for loss resistance. It is depend on the material used in the antenna, okay, the construction and the operating frequency. So in short, there's no way that we can calculate the loss resistor. Okay, as I mentioned, for example, heat energy, okay, how much will be converted to heat is almost very difficult to calculate, and also the conductor loss and dielectric loss probably we can calculate, but the heat loss probably will be harder to account for. Okay, so one of the example, okay, loss resistance is typically very, very small, okay, but can be quite significant in real world antenna, okay, especially through at lower frequency, okay, where conductor loss become more severe. Okay, let's move on to the reactance. Okay, so basically this will be the last impedance. Come to the definition. Okay, reactance is actually a measure of an antenna opposition to change in current or voltage due to its inductance or capacitance. Okay, in another word, okay, it describes the energy stored in the magnetic or electric field around the antenna. So basically, this reactance is basically to describe, okay, the energy stored, okay, nearby the magnetic or electric field that is generated by the antenna. Okay, the reactive, okay, they can be either inductive or capacitive. Okay, it determines how the antenna impedance effect is matching with the transmitter or receiver circuitry. Okay, for resonant, okay, reactive, ideally it should be zero. Okay, so this is what we have mentioned earlier on. Okay, in order to have maximum power transfer, in order to have a match constitution, okay, so basically this reactive, basically they need to be in zero, okay, which means that zero, nothing on the X or imaginary, mean that the inductive and capacitive reactance actually cancel each other. How to achieve zero is, for example, if we have inductive, okay, basically we need to have another capacitive reactance to cancel away the inductive. Or for example, we have a capacitive reactive, then we need to have insert another inductive reactive in order to cancel away the capacitive reactive. So what is actually inductive reactance? Okay, so basically this occur when the antenna actually behaves like an inductor, okay, causing the current to lag behind the voltage. As for capacitor reactance, basically this occur when the antenna behave like a capacitor, causing the current to lead the voltage. Okay, so basically this is a very simple definition. We are going to take a close look, maybe not on the next few video, okay, but definitely we are going to take a close look of inductive reactance and also capacitive reactance soon on this antenna discussion. Okay, so as for the SI unit will be the same, will be under the ohm. Okay, I guess you know how to calculate this inductive reactive here. Basically, it's shown over here. Okay, same for the capacitor. Okay, so for example, okay, if the antenna is too short, okay, as compared to the wavelength, okay, it may have capacitive reactance. However, when the antenna is too long, okay, it may exhibit inductive reactance. So basically, this will be the discussion on the last impedance, which is the reactance. Okay, let's do a very quick conclusion here. Okay, in order to have impedance matching, okay, for maximum power transfer, okay, basically for efficient signal transmission or reception, okay, the impedance of an antenna must match the impedance of the transmission line. Okay, any poor impedance matching, this actually led to signal reflection. And once we have signal reflection, we actually reduce our efficiency. Okay, we talk about resonant. Okay, so basically when we actually at resonant frequency, okay, the reactive or the imaginary part will become zero. Okay, so this is what we have discussed earlier on. In order to achieve maximum power transfer, okay, we need to remove away whatever the reactive component or the imaginary term. So they need to be zero. Okay, which means that the impedance is purely resistive. For example, 50 ohm. Okay, no, nothing on the J term. Okay, all the imaginary term are all zero. Okay, so as I mentioned, this will outcome the maximum power transfer. Okay, the antenna impedance is actually critical for communication system performance. Okay, to achieve maximum power transfer from the antenna to the receiver or from the transmitter to the antenna. Okay, the antenna impedance must match the system impedance, which I have emphasized many times. In RF and microwave system, the typical system impedance are 50 ohm. I will say 50 ohm is much more common as compared to 75 ohm. Okay, most of the equipment, for example, they are all so-called source impedance is actually all at 50 ohm. So basically 50 ohm is definitely more popular or more general, okay, as compared to 75 ohm, okay, which correspond to the characteristic impedance of standard coaxial transmission line. Okay, remember coaxial cable typically will be like 50 ohm most of the time. We definitely also have some 75 ohm coaxial cable, but in general, okay, most of the coaxial cable, they are actually all 50 ohm. Okay, the antenna impedance will also limit the bandwidth of the antenna. So in short, okay, how well you actually adjust on the antenna impedance, this actually will affect the bandwidth of the antenna also. Okay, so before I end this video, I like to quickly show you this. Basically, will be on the antenna impedance. Okay, for both the transmission and also receiver mode. Okay, maybe on the next video, I will discuss this in more detail. So with this, I like to end my discussion. Okay, please help to like and subscribe. Once again, thank you so much for your strong support. I hope to see you guys soon. Bye for now. Thank you.